For a normal semester, we are supposed to cover chapter 9 and chapter 10. But I don't think we will have time to cover chapter 10 this semester. Both chapter 9 and chapter 10 are applications of first law and the second law. We have analyzed the devices by using the first law and the second law. This chapter, we can utilize what we have learned to analyze the device efficiency and the overall heat engine and the heat pump efficiencies. These are the purpose. And the chapter 9 covers the working fluid, which involve phase change. We are going to use two idealized cycles, Rankine cycle, vapor compression refrigeration cycle, as prime examples to illustrate how these principles we learned before can be used to analyze these cycles in detail. Keep that in mind that in this chapter, both heat engine and heat pump involve phase change as the working fluids. For an idealized Rankine cycle, it involves 4 segments like we have been discussing. However, this 4 segment of the process involve 2 adiabatic compression and isobaric heat exchange. If we start from the fluid after the condenser, it's pumped into the boiler, absorb the heat, then the steam comes out, moves the turbine, does a lot of work, and the steam comes out, the turbine will have a lower enthalpy, and that the residual heat will have to be absorbed by condenser. That completes a full cycle. We assume that the turbine and the pump are operated in the adiabatic conditions, and the heat absorption in the boiler and the condenser are constant pressure. The pump will have to push the fluid into high pressure heat exchanger to absorb the heat. And similarly, the condenser is conducted at constant pressure. And for an idealized Rankine cycle, we assume that all the segment of the entire cycle is operated in the reversible conditions. And to learn this subject well, we should always link what we assume, the actual diagram of the devices and the TS diagram. When the fluid is pumped into the boiler, the temperature increase due to the pump power given to the fluid. It's adiabatic, so it give away the pump power to the fluids. So the temperature will rise and push into the boiler, and the boiler is operated in the constant pressure conditions. We learn in the earlier chapters that on the TS diagram, constant pressure line represents something like this. And then if the fluid come out of the boiler as a saturated steam, then it can be it can do some work. Turbine will do some work so that the temperature drops. And during the condensation process, the fluid change its phase. So the cyclic process can be represented by 1, 2, 2 plus 3, 4, 1. This is the standard Rankine cycle, idealized Rankine cycle. Alternatively, we can also push the fluid to superheated steam. Then it will do more work in the turbine side. So if the exceeding stream from the turbine is a two-phase fluid, then it's located somewhere in a horizontal line like this. So the complete cycle will be 1, 2, 2 prime, 3, 3 prime, 4, and a return to 1. And one of the important characteristics of the fluid on the TS diagram is the fluid after the condensation is usually saturated liquid. So it's on the phase line. And if we further assume it absorbs the heat in the boilers so that it reaches the saturated vapor state, then state 1 and state 3 are saturated liquid and saturated vapor. So we can say x1 equal to 0, x3 equal to 1. If we can let the steam absorb more heat so that the steam reach superheated conditions, then temperature will rise further, but it will remain as a constant on the constant pressure line. If we analyze the standard idealized cycle, 1, 2, 3, 4, and a return to 1. Let's look at how many variables we need to stipulate before we can analyze the fluid states at all these 4 points. We already know this process is assumed to be in the steady state. It's reversible, so there's no entropy generation. 2 of the segments, the pump and the turbine, are operated in the adiabatic condition. So Q equal to 0. Also, it's very important to remember we discussed this couple places, like last chapter, we discussed the shift work for this segment, for turbine and the compressor. The shift work is the integral of VDP. On This diagram may not help us to estimate this quantity, but we'll see later on the PV diagram, we can get these two quantities very easily as the rectangular area of PV diagram, on the PV diagram. And so the fluid has 4 states, 1, 2, 3, 4. So there are 8 variables altogether we need to stipulate. However, we already identify 4 process equations. Adiabatic, that means Q equal to 0. Isobaric, constant pressure lines here and here. So we have 4 assumptions imposed in the for the process equations. And we also have 2 more assumptions that the fluids have x1 equal to 0, x3 equal to 1. Therefore, amazingly, we need only 2 conditions to stipulate before we stipulate everything else in the cyclic process. Usually, and this is what we are going to discuss in the example. Usually, we designate T1, the temperature of the fluid before it's compressed to the boiler. Temperature and the pressure inside the boiler. We usually stipulate T1 and the P2. So everything else is known. Let's think this way. If T1 is known, because it's on the saturation line, can we find out the pressure? The answer is yes. Saturation pressure will be the pressure at this state. Now, for state 2, we are given the pressure, but the entropy is the same as state 1 because it's an isentropic process. So state 2 is fully determined. For state 3, we already know the pressure is same as state 2. It's a saturation state, so the temperature can be found from the steam table. Now, from state 3 to state 4, it's an isentropic process, so the entropy for state 3 will be the same as state 4. And since the temperature of state 4 is identical to state 1, remember this is a horizontal line. When it returns, when the fluid condenses, temperature doesn't change. So I just illustrate, if we are given T1 and a P2, all the 8 states can be found. Now, we also discuss the situation where the state 3 is pushed further to 3' to superheated state. Then additional condition will have to be given. Usually T3, the temperature it reaches. So this is one variant of the problem. The other type of variant of idealized Rankine cycle is assume this compressor and the turbine are not operated in the idealized conditions. They are not reversible. So usually we have to know the isentropic efficiency of the turbine. If we are given the isentropic efficiency, we can estimate the actual location of state 2. Based on what we learned from the last chapter, we know state 2 will be located on the right-hand side of this vertical line. Similarly, if the turbine is not operated in the isentropic condition, it's not reversible, state 4 will be on the right-hand side of state 4 on this horizontal line. It will go not vertically down, it will be a straight line like this. So these are the two variants in solving problems. Now let's analyze the Rankine cycle in the following way. Before we discuss the detail, we can discuss how superheated steam can be achieved. If normally the steam come out of the boiler as saturated steam, we can route the steam back into the boiler to absorb additional heat. So 3', the steam come out will be superheated steam, 3'. So this is one type of variant of the problem. And if we use what we have learned earlier this semester to analyze the full cycle, we can write the first law and the second law in a very compact form. I believe most of you are already very, very familiar with the use of first law and the second law. So all the heat energy equations are for open system and the steady state. So we use the energy balance equation we learned back in chapter 4, simplify. We can eliminate the kinetic energy term. We can eliminate the potential energy term for the total enthalpy. We can assume the process operated in the adiabatic condition, so there's no Q term here. For the boiler, we don't have work term. Instead, we have Q term. For turbines and the condenser, we have two energy balance equations similar to the pump and the boiler. So these are for the energy balance equation. For the entropy balance equation, operate in the steady state, open system operated in the steady state, entropy of inlet minus entropy of outlet plus heat transfer term plus entropy generation term. Since there's no heat transfer in the compressor, in the pump, that term is 0 because the pump is operated in the reversible condition. There is no entropy generation. So this is a simple entropy balance equation for the pump. For the boiler, we have a heat transfer, but still, if we assume it's a reversible situation, then we don't have to include the entropy generation term. And finally, the turbine and the condensers, the two equations are similar to the two entropy equations for the pump and the boiler. Now, if we combine all the energy equation, combine the four, it's interesting to know all the entropy terms disappear. So we get the equation, the turbine work minus the work done by the pump equal to the energy provided by the boiler minus the energy released to the condenser. And furthermore, these two integrals of heat transfer term can be simplified to algebraic expression because we have some temperature in the boiler and the condenser are constant. Finally, we have to know the definition. Conversion efficiency or thermal efficiency of an idealized Rankine cycle, by definition, is the net work performed, that's this quantity, net work performed divided by energy absorbed from the boiler. As an investor, we are always interested in this efficiency. And this equation we have seen before, 1 minus QL divided by QH. Now, if we look at the diagram, the states on the PV diagram, it can be drawn like this. From state 1 to 2, it's a vertical line up. State 2 to 3 is a constant pressure line. The turbine does work, and it reaches a point, horizontal line, because it's isomes, constant pressure line. Then this makes the estimation of pump power very easy to estimate. It's this rectangular area is the pump power. Then on this slide, we enhance our discussion to superheated state 3. The analysis will be similar, except we need a third variable to fully stipulate all the states. For the pump, it's the same. Energy equation, entropy equation, but for the state 2, pressure the same, entropy the same. Now, in order to estimate the work, we use VDP, the pump power, like this, because it's a liquid, it's essentially incompressible. The specific volume remains constant during the pumping process. It's a vertical line up because specific volume remains the same. We have learned from the last chapter, the pump power, the energy required to successfully pump the fluid to this high pressure is the rectangular area. So we can use this algebra expression to estimate the energy required for the pump. Alternatively, here I said we can also use the property table because entropy remains the same in this vertical line process on the TS diagram. We can find the property of state 2 easily. For the boiler, we have enthalpy difference between state 3 and the state 2 equal to the energy being absorbed. Entropy equation generated S3 minus S2 equal to integral of dq over T. Because the final temperature has to be given for superheated state 3, so the state 3 can be fully given in the sense the temperature is given, the pressure is the same as state 2. And the analysis of the turbine will be the same. Now let's look at a specific example. If we have a basic Rankine cycle, no superheat, if we are given the pressure high pressure 2 megapascal, that's P2. This is constant pressure line. 2 megapascal, and a condenser pressure of 10 kilopascal. We are asked to find the thermal efficiency. So notice we are given only 2 pressures. So high pressure and low pressure process. This condensation also take place at the same pressure. State 3, state 1 have the same pressure as state 4. So we can start from pump. The fluid entering the pump, we are given the pressure. Because it's saturated steam, saturate water at that pressure. So we know the temperature. So we can find the property fully for state 1. For state 2, because it's the work can be the integral of this area to the left of this triangle line. So we estimate the W term. Once we know the W, the first law allows us to calculate enthalpy at state 2. So state 2, we know the pressure, we know the enthalpy is fully defined. For state 3, because we know the pressure is given in the problem statement, and we can use the saturated vapor to calculate the temperature. This is on the saturation line. So temperature is known here too. Then for the turbine, it's a vertical line down entropy for state 4 equals the entropy for state 3. Furthermore, the pressure is known, so everything else is known. So that fully determines the state. If we can find all the properties, including the heat transfer term, some of the heat transfer term, we have to rely on the Q. Q can be estimated based on the first law. So the thermal efficiency of this thermal engine can be estimated based on the definition. From here to here is the first law for the numerator. And we can insert all the conditions we found, the properties we found in the calculation. So this is a standard problem for Rankine cycle. Here at the bottom, I like to remind you to think about if we can start from state 3 for the analysis. The answer is yes, because it's saturated steam. The pressure is given, so the temperature is known. And from its entropy, we can calculate the entropy, and the pressure for this process is, for state 4, is known too. So we can estimate the quality for state 4. So we can do similar calculations for state 1 and 2. Now, the next example, we have a Rankine cycle. We are given the high pressure coming out of the boiler. This is where the fluid stays inside the boiler. Either we are given the condition, pressure, temperature, and the flow into the turbine, and the condenser at the low pressure, 10 kilopascal, that's given here. So we are given 3 pieces of information. We can estimate all the fluid property at the 4 states. We can also estimate the thermal efficiency based on the definition and the first law. So we can again start from the saturated state, because we are given the pressure, 10 kilopascal. On the saturated liquid line, we can find the pressure. Vertical line up, we can find the entropy, and the pressure is known. And then for the process from 2 to 3, the pressure is given, the temperature is given, so state 3 is fully given. And if state 3 is fully given, entropy of state 4 and is known, and the pressure for state 4 equals the pressure of state 1, that's 10 kilopascal. So that completes the analysis of a full cyclic process. All the property can be estimated. Then the efficiency can be estimated based on the definition, that is the work, net work done divided by the energy absorbed at a high temperature. Based on the first law, the numerator can be replaced by the difference of QH minus QL, so we can calculate the thermal efficiency. And the third example is a similar example to the last one, except the units are given in British unit. We are given the pressure inside the boiler. we are given the temperature of state 3, we are given the pressure before the fluid entered the pump. So the solution algorithm is very similar to the last example, but I do want to caution you, the conversion of units could be troublesome, like from PSIA to this energy units is something you have to be able to solve. Now let's look at a refrigeration cycle. A standard refrigeration cycle we call vapor compression refrigeration cycle. This 4-segment process is similar to what we discussed earlier. Fluid enter the compressor and release the heat. This heat release includes the pump power and the heat absorbed from the cold zone. Then the fluid return to the cold zone through a nozzle or an expansion valve. So the fluid expand and then absorb the heat, return to the compressor and release the heat. In this 4-segment, the only difference from the heat engine in terms of the assumption, we do assume there is a adiabatic compression, that's for the compressor. There are 2 isobaric constant pressure process for heat transfer. But for the throttling, as we learned earlier, throttling is, in many cases, we can assume it's a constant enthalpy process. So we call isenthalpic expansion. That means enthalpy doesn't change from state 3 to state 4. And still, based on similar analysis we did for the heat engine, we only need 2 conditions in order to fully stipulate the entire cyclic process. And usually we are given T1 and the P2. Let's look at how we can analyze the system. Again, we have a set of 4 energy balance equations. Notice the only equation which is different from the heat engine is we assume the throttling process is a isenthalpic process. The enthalpy remains the same. And for entropy balance equation, because when the fluid passes through a compressor, heat transfer term is no heat transfer, adiabatic. So it's 0. We also assume the process is reversible. So there's no entropy generation. For condensation, for state 2 to condenser state 2 to state 3, we release the heat at the high temperature. There is a heat transfer, but it's still reversible, so we don't have entropy generation. For constant enthalpy process, since it's still adiabatic, there's no heat transfer term, but we're going to have an entropy generation term. So this is different from the idealized heat engine. Then the evaporator process is same as a heat engine. We have a heat transfer term, assume adiabatic, so assume reversible, so we don't have the entropy generation term. For a refrigeration cycle, we have two COPs. One is for the refrigeration only. That means QL divided by the work done by the compressor. So this is how it's defined. And from the last chapter, we know from the detailed analysis of shift work, we can replace Q term by enthalpy term. And for the COP for the heat pump, entire heat pump, is QH divided by the work done on the fluid. We can use similar calculation to estimate COP for heat pump. However, we can also use this relation, COP for the heat pump equal to beta for the refrigeration cycle plus 1. Here is an example. If we are given the temperature of the refrigeration cycle and the high temperature, the heat is released at a high temperature, 40 degrees C. We are given the mass flow rate. Then we are asked to solve the flow state completely and then estimate the cooling capacity of the cycle. Cooling capacity means heat being absorbed at the low temperature reservoir. So again, we can start the analysis from the compressor, state 1. Since the temperature is given, we know the pressure, so the state is fully given, including enthalpy and entropy. From state 1 to state 2, it's an isentropic process. So it's a vertical line up. Since we are given the temperature, we are given temperature for this horizontal line. But the temperature of state 2 can be estimated because we know the process is isentropic. So entropy of state 2 is known. So we can estimate this line represents constant pressure line. So pressure of state 2 equal to the pressure at the state 3. This is a saturation liquid line. So the pressure can be found from the saturation table. So if this line is constant pressure line, state 2, we know the entropy and the pressure. So state 2 is fully given. State 3, we already mentioned, since the temperature is given 40 degrees C, it's on the saturation line. So all the property can be found from the saturation table. Now from state 3 to state 4 is a constant enthalpy line. There will be entropy generation from state 3 to state 4. Therefore, we can find the state 4 conditions, constant enthalpy from state 3 to state 4. State 4's temperature is known. So state 4 is fully stipulated. Then we can find the efficiency based on the definition, QL divided by WC. Okay, and the cooling capacity, the rate of heat transfer at the low temperature reservoir from state 4 to state 1 can be estimated based on this first law times mass flow rate, which is given in the problem statement. So this completes the requirement for chapter 9. And chapter 10, we plan to discuss, if we have time, the heat engine and the heat pumps for with working fluid doesn't involve phase change. They are purely gas phase. This concludes this particular lecture.